Hey, calculus students, and welcome to our second introductory video leading into our portion of the course on series. And the idea here that we're kind of building on to get started is the idea of approximating some function with a polynomial. Now, in the first video of this pair, we approximated the natural exponential function with a linear function. So that's just a linear approximation, like in Calculus 1. We saw that we were able to do that. We got a linear function that had the same value as the exponential function at 0 and had the same slope as the exponential function at 0. So that was great, but as far as getting a real accurate approximation, you figure, well, maybe we want to do a little better than that. Because of course a line, it's straight, it can't curve, and most functions have graphs that curve. So, getting on with that idea, let's see what can we do if we want to get a better approximation to our function. And we'll stick with the natural exponential function for now. It's a nice simple one to start with. Okay, so what if we could get an approximating polynomial that not only has the same value as our function at 0 and the same slope as our function at 0, but also would bend the same way. Now, bending the same way, of course, seems like kind of a vague term, but you probably figure that has something to do with the second derivative, and it does. Okay, it's related to the concavity of the curve, and here we get a little more specific with concavity than just concave up and concave down, but we actually can quantify exactly how curvy that curve is. And this involves the first and second derivative, so we're going to need to get that second derivative to match as well. Okay, and to do that, we're going to need to kick things up to a quadratic polynomial so that it can have the same second derivative at 0 as our exponential function does. Now, you might wonder, well, why can't I get a line to do that? I mean, maybe it's obvious, since as we said, lines can't curve. But I claim that a linear polynomial could, in general, never match the value of a function's second derivative at a point. Okay, and think about that. You can pause if you like. What is the second derivative of any linear polynomial? Well, you differentiate it twice, everything's going to be gone. Linear functions have second derivative 0, so unless your function that you're approximating has second derivative 0 there, which, might kind of tell you it's a line anyway, we're going to need something beyond linear polynomials to do that. Quadratic work. Okay, so to start out, we got, kind of a blank slate here, you might say. Our second degree polynomial, it just looks generic here. Notation for it is t sub 2 of x. That's a degree 2 Taylor polynomial. And it's going to be a constant term, c0, plus a linear term, c1x, plus a quadratic term, c2x. And all we have to do is find out what the c0, c1, and c2 are. And so that's what we'll get into on our next slide. Okay, so there again is our form. And again, the whole idea of this is that we want to keep the value and the first derivative matching and get that second derivative to match as well. Okay, so let's crank out some computations and see how to do that. So for T2, T2 of 0, if we put 0 into our generic expression, general expression for T2, the last two terms are going to go away. That's just going to be C0. So T2 of 0 is C0. And remember here, I should probably put it up here, f of x is e to the x. We're still working with our base e exponential function. And so you know as well that f of 0 is equal to 1. Okay, well now if you put those two things together, we know that we want the values of these two functions at 0 to match. And so we must have that c0 is equal to 1. Okay, wow, that was easy. If only it were that easy to find the other coefficients just by kind of plugging in. It couldn't be that easy though, right? Or could it? Well, it almost is, because we can actually get those values by plugging in. We just have to differentiate first. Okay, so to find C1, let's take our derivatives. So we need to do T2 prime. Well, okay, let's do T2 prime of x first. Get that out of there. T2 prime of x, well, you differentiate, the C0 term is going to go away. In the second term, the x is going to go away. We got C1, and then we got 2C2x. So there's the second derivative of our general Taylor polynomial. And if we put in 0 now, T2 prime of 0 very conveniently turns out to be C1. Okay, and what about on the other side? Well, f prime of 0. I don't think there's a lot of mystery to this. That's the exponential function. You differentiate it. Still the same exponential function, so when you put 0 into it, we get the same thing that we got before. Like I said, simple example here at this point. So f prime of 0 is equal to 1. We know we want to equate those together. Okay, we want that t2 of 0, or t2 prime of 0 and f prime of 0 to have the same value. And so we got to have c1 equals 1. All right, so far so good. All we need now is c2. Guess how we're going to find it? You probably guessed. Keep things easy here. We're going to differentiate again to get those second derivatives to match. So the second derivative of t2, we take the first derivative, we differentiate it again. Now the c1 is going to go away, and the x is going to go away, and we just have 2c2 for our second derivative of the degree 2 Taylor polynomial general form. And really, there's not a lot that happens when you put 0 in here. We'll do it anyway, because, of course, it's a constant function. Anything you plug into it, you're just going to get that same constant back. So t2 double prime of 0 is 2c2. And then the exponential function's derivatives keep that nice consistency, as they tend to do. So f double prime of 0 is equal to 1. And now if we equate those, we've got 2c2 equals 1. And we got a little bit of solving to do this time, so that c2 ends up being 1/2. Got to divide that 2 over to the other side to get c2 by itself. All right, there we go. We have now filled in, or we can fill in, to our general form degree 2 Taylor polynomial, we can fill in the coefficients that we found and find that for our base E exponential function, t2 of x is equal to 1 plus x squared over 2. Awesome. So now the idea is that this should be also kind of curving the same way that the exponential function does right at t equals 0. Okay. So let's compare. Let's see how the degree 2 Taylor polynomial compares to the graph of our exponential function. There it is again. E of x should be approximately equal to t sub 2 of x. And what we can do is we can take a look at Desmos and see how they compare graphically. And then we'll do it with table form as well. Let me get that set up. Be right back. All right, here we got our graph in Desmos. You can see in red there the graph of our base E exponential function. The linear approximation that we got last time is right here in blue. Yeah, you can see the graphs align, and it does stay fairly close to the graph of our exponential function in that vicinity of the y-axis, which is that slightly darker line there. Now, of course, as you know, you zoom out and, ooh, yeah, that line is not such a great approximation anymore. Once you get anywhere very far away from 0, let's say like more than 1 away from 0, it's just not good at all. Let's see if the degree 2 Taylor polynomial approximation does better. Okay, there it is in green. And you can see that, yeah, it does. It's curvy for one thing, and it actually stays fairly close to the graph of that exponential function. Again, not super long term. Again, it starts curving away. It curves back up, where if you go over to the left, whereas the exponential function, of course, keeps going down and approaching the x-axis. On the right, again, it looks fairly good. The exponential function starts increasing faster, as exponential functions tend to do as you go up there, so they get further apart. But you can see that certainly the degree 2 green approximation is a lot more realistic and more accurate than the blue degree 1 Taylor polynomial approximation. And as we zoom in again, of course, the more you zoom in, the greater accuracy everything's going to have, all approximations. But if we look at on this kind of a scale, you can see, yeah, the green, the degree 2 green one is pretty much right on top of the graph of the exponential, whereas the blue one, you can already see that it's verging away, even on this kind of small scale. Okay, so degree 2 is helping us out quite a bit here. Okay, let's see. We looked at Desmos. Let's look at a table of values here. So here we can compare the actual value of e to the x. Actual, of course, we've rounded everything to 6 decimal places. And I put the T1 values there for comparison as well from the previous video, and then we've got our T2 values here. And the errors you see are, again, rounded to 6 decimal places, and they're for the T2 approximation. And if you go back and compare, well, I mean, you can see the T1 values here. The errors are quite a bit smaller. Now, of course, by the time you get to 3, the degree 2 Taylor polynomial approximation is also pretty far off from the actual value, even though it's somewhat closer than the linear one was. But right near that center of the Taylor polynomial approximation, we do get improvement here, as we would hope and expect, since the degree 2 Taylor polynomial is also bending the same way that the exponential function does at 0. That's going to help it stay closer for longer than the linear one can. Okay, let's see. So how about in general? We did one specific example. We want to generalize this to a procedure that will work for any function that is differentiable enough. And what we saw here for our coefficients of the degree 2 Taylor polynomial, they were f of 0, f prime of 0, and f double prime of 0 over 2. And there's really nothing special about our exponential function base e. That is always what is going to happen. As long as your function's differentiable enough, it's got to have at least up to a second derivative for this process to go through. But if it does, it's going to work out the same way. You're always going to pick up that 2 in the second derivative, or when you differentiate the general form and so on. So you're always going to have that 2 in the denominator. It's always going to work out this same way. So we can give a general definition of a degree 2 Taylor polynomial for f centered at a. And here it is. You can see our general form pretty much like it was, but then we got our coefficients now settled in here as well. And this is for center at a. Again, we did center at 0, but center at a, it's still going to be the same kind of thing. You just need, if you want things to match up at a, you need to evaluate at a, which might be some other value than 0, but otherwise everything's going to work the same way. Oh, you've also got the x minus a's in there. Yeah, that's a little bit different as well. I think one of the morals here is that if you want to keep this Taylor polynomial stuff as simple as possible, centering at 0 is going to be helpful in that, because when we do center at 0, then we get something that looks a lot more like the example we just did. We got x and x squared, no minus a's in there like you have in the general form. And again, those x minus a's are essential to getting our process to work out just as nicely when we are centered elsewhere besides 0. Okay, so where is this headed? Where will we take this in class? Well, we'd like to generalize beyond just, general function. We'd like to do general degree as well and get a formula for a degree n polynomial that approximates our function as well as possible. Okay, so using higher degree polynomials, it seems reasonable to expect that higher degree polynomials should give us increasingly more accurate approximations of our function f. Again, near the center, that's we gotta not set our expectations too high, but near the center they ought to be get to be better and better approximations. And a general Taylor polynomial like that of degree n is going to have this kind of a form. You set it up just like we did for the degree 1 and degree 2. We just got coefficients c0 through cn now, so there's more to find. And how do you find them? Well, we want them again to satisfy this criterion that they make the first n derivatives of the Taylor polynomial match the first n derivatives of our function f, and these are again values at the center. Here we've specialized the center as 0 again, just to keep that notation a little cleaner for the moment. Now, beyond the second derivative, the geometric or visual meanings of the derivatives certainly become a lot more subtle. For instance, the third derivative will tell you, like, it'll measure how fast the concavity is changing. May seem kind of esoteric or eccentric kind of thing to think about. But the point is, the more you make these derivatives agree at the center, the more that's going to keep the behavior of the two functions alike around that center anyway. Their behaviors should be closer to the same, and then the longer the graphs of the function and the approximating Taylor polynomial should stay close to each other. And so in class, what we're going to do is we're going to take this idea, run with it, and look at higher degree Taylor polynomials with, again, the temporarily kind of presuming that they're going to give us something more accurate. We'll find out that really is the case. And eventually we'll see how to quantify that. Well, you know, we know how to quantify it with the error, but we'll see more kind of precisely that, yeah, that is in general going to happen. With higher degree, we're going to get better approximations of our functions. But how do we find all those coefficients? Taking it one by one could be a long and tedious process, so we'll try to kind of speed up that process into more of like a little bit like an assembly line kind of thing. So we'll see how to do that in class, and we'll see you there.